Anyone else hearing a beeping noise? No, it's not feedback. Unfortunately, the video last time got cut off because the battery died. So I'm going to start switching the battery at break. So hopefully that won't happen again. Okay. So just want to, again, this is kind of vocabulary you should know. If you have an equation such as familiar with things like that, we refer to the solution of this as a root or a solution, or sometimes a zero, because if I were to graph this, y equals this, where it crosses the x-axis, it's 0, it's a 0. Okay, it's just some basic vocabulary. I kind of gave up yesterday on long division. I want to go over that. It's important. If you know how to do this, I'm sorry, we're going over the whole stuff. But if you're all not familiar or not happy with your ability, please just don't leave it here. So how do we divide this by? We're lucky it's just a linear function. So there's two ways to do this. One way works whether this is linear or not. The way we're going to do it first, which is long division, very similar to long division of numbers. Take a look here. X goes into x cubed, x squared times. The way it's easier than with numbers. Just with numbers, you sometimes have to guess. Here we don't really have to guess. This is x cubed minus x squared. Here's the part that gets people messed up. -6 minus -1. -6. That's -6 plus 1. -5x squared plus 11x. We bring this down. Minus 5x. So x into minus 5x squared is. So this first term is always going to disappear. -5 times -1 plus 6x. Okay, the subtraction is a little easier. Oh, sorry, 5, 6. Anticipating x minus 6 and plus 6, 6x minus 6. So we have remainder 0. So we know this divides evenly. Now this is nice in conjunction with the rational root theorem, which told us that the roots, because this is a 6, can only be 1 plus or minus 1. It can be, since this is 1, the numerator is always going to be 1 plus or minus a half, plus or minus a third, or plus or minus 6. So we can try these, see if they're roots. In this case, I just said, well, let's try the obvious one, 1. 1 minus 6 plus 11 minus 6 is 0. So we know 1 is a root, and we can divide by x minus 1. And once you get something down to a quadratic, that should be pretty easy. You always use the quadratic formula to find the roots. Okay. Well, excuse me, I'm having, I think it's an oxygen. Take a break here. Oh, okay. So that's roots. Oh, I guess for those of you who remember synthetic division, that can be really nice, right? If you get it right, the computation looks it's exactly the same computation, but it's easier. I'm just going to demo it. For those of you who are unfamiliar with it, you might be enticed to learn it. So we take the coefficients here, and we write them here. 1 minus 6, plus 11 minus 6. And we take the root, not the minus 1, but 1, and we put it here. We bring 1 down, the first number. We multiply, and put this number here and add. And we just keep doing that. 1 minus 5, 6, 1, 6, 0. Okay, so this tells us that the result was x squared minus 5x plus 6 with a remainder 0. You can see a lot quicker, a lot less writing. If you want to learn synthetic division, you don't know it, come to my office hours, come to the Tuesday, Thursday stuff. You know, we'll teach it to you. It's useful. And it only works with a linear factor, so it has its limitations. You still need long division at times. Okay, we talked about the quadratic formula. This is the solution to ax squared plus bx plus c equals 0. And I wanted to focus on this particular piece of the quadratic. B squared minus 4ac has a name. It's called a discriminant. And it tells you about the roots. If b squared minus 4ac is 0, you have one unique root. It's really a double root. This is, you have a graph, your parabola just sits on the x-axis, and that's when you get this is 0. If b squared minus 4ac is greater than 0, you're going to get 2 real roots. And if it's less than 0, you're going to get 2 complex roots. Complex numbers that involve square root of -1 imaginary numbers. I'm not going to talk much about imaginary numbers because they don't come up very much in calculus. In calculus, we're mostly dealing with real numbers. So, you can think of this as no roots, I guess. This is what happens if your parabola is either below the x-axis and you don't cross the axis, and so you don't get any roots. Okay. I did mention briefly inverse functions. I just want to, there's a couple more things I wanted to say about them. Let's take a function f of x equals x squared plus 5, and I want to find the inverse. I'm not worried yet about the domain. Remember, you have some parabola here, you want to find its inverse. Well, this passes the vertical line test. But as you see, when we kind of switch this over, it's going to fail it. We can adjust the domain. So we're not interested in this part, so now its inverse will be a function. But what's the process to find the inverse? Well, this is the way I go about it. I write this as y equals x squared plus 5. That's step 1. Step 2, I switch x and y. So I get x equals y squared plus 5. And then I solve for y. Solve for y. Okay, so how would I do that? Subtract 5 from both sides. Find the square root. And there I have my inverse, at least the inverse mapping of the function. And this is going to work easily for most functions, not all. Some functions you're going to have to, you might have to think a little harder. I won't put those on the exam because we don't want people fainting. Now, one other thing you should know about inverse functions has to do with their graphs. If I have a function, f of x equals x squared, and again, I'm going to specify the domains as x greater than or equal to 0, and it's a parabola that looks like this. The inverse mapping of the function is going to be the square root of x, which is going to look like this. And you might notice right away that you draw this line y equals x. These appear to be mirror images, which is always the case. If I have a point here, xy, there's an equivalent point here, which I'm not going to, which is going to be yx. So that's a good thing to know when dealing with inverse functions. I feel like I'm rushing along. You're welcome to always, slow me down, ask me questions. This is review, so I'm assuming a lot of you know this. Again, if you have any questions, don't feel shy. Okay, I'm going to deal with just a couple, really just definitions that you should be aware of. We have functions which are increasing. Intuitively, if you look at the graph, as you go from left to right, it only goes up. And the definition we use for an increasing function is A is less than B, then for all A and B, then A is less than B, then f of A is greater than or equal to f of B. Likewise, we have a decreasing function. If A is less than B, then f of A is less than or equal to f of B. All right, that would just be a function moving downhill. There's also a slight nit that I don't think we're going to need to worry about. There's something called a strictly increasing function and a strictly decreasing function. And the only difference is you kind of remove the equal sign. Strictly increasing means it doesn't flatten off and then go up. It has to always be going up. Okay. I wanted to define and describe what a rational function is. So we've already talked about a polynomial function being the sum of monomial terms. And a rational function consists of a polynomial divided by another polynomial, where q is not a constant function. So, for example, x cubed plus 5 over x squared plus 2. That would be a rational function. Change that a little. Now, there's a common thing that students are taught in high school and some pre-calc classes. We have this as a function. The question is, what's the domain of the function? Who here has run into a question like that and knows the answer? Yeah.
Wouldn't it be at the bottom?
It has to do at the bottom, yes. Okay, I don't want to pursue this because it's really, yes.
Well, the denominator can't be 0?
Well, the denominator can't be 0. Can't be part, 2 can't be part of the domain. Right? But people say, what's the domain? And they say, well, it's all real numbers without 2. Well, that's a convention. We just decided that if you don't know what if it doesn't say what the domain is, it's everything it can be. But functions are not functions without domains. This by itself, even though I've expressed it that way, and I will, it's not a function, it needs a domain. If I haven't specified it, well, that's the convention we use. In this case, all we have to do is say the domain is all real numbers not equal to 2. So, now, when you're looking at a rational function like this, and you see there's a member of the domain missing, in this case 2, you're going to get an asymptote there. So, I don't know what this function looks like. Oh, I do. I know. we could graph some points. 3, a big number. 2, oh, it's an even bigger number. I think it's going to be something like this. And then 0 is going to be negative. It's probably going to be like this. Now, there's a few other details to talk about here, and I don't want to talk about this function. So, I want to talk about this function. So when this gets very large, what does this look like? It kind of looks like x. So if we're over here, it's going to look like this. When x is very small, it's also going to look like x. So what happens between here and here? Well, that's a different question. We can see that at 0, it's 5/2. It's going to go to this point. So it's going to curve a little. But these are its end behavior. And you can tell pretty easily the end behavior by just looking at the leading term, right? There's a lot more to say about this, but again, if you're unfamiliar with it, we can talk about it in a different venue. All right. kind of skipped over exponential functions and exponential function, 10 to the x or e to the x. You should know that an exponential function looks like it's going to go through 1. It's going to go up. And any function of this form is going to look similar. The shape is either going to go up faster or come down slower or slower. The inverse function of an exponential function is a log function. We write it this way, or in the case of log to the base e, we have a special name. It's the natural log, and we'll write this as ln dx. And being inverses, you can kind of see if I can get this right. You can just kind of draw a mirror again, and you get, in my case, a poorly drawn, but a log function. One really important skill you're going to need is, if you don't have it already, is to know all the rules for handling exponents and logs. I'm just going to go over some basic ones. You should know that a to the n times a to the m is a to the 90. A to the n over a to the m is a to the square root of a is a to the, anybody doesn't know this, pay attention, this will happen to you. Yes? Yes? 1/2. Any root, a to the n, is a to the 1 over n. There's a few more you should be aware of. I'm not going to redo pre-calculus here, but be aware you need to know how to handle exponents. Now logs, in a very fundamental way, since it's an inverse, we're just the opposite. If I have the log of a times b, anyone remember how am I going to divide that up? It's going to be the log of a, and then what?
Over log.
Good guess. Wrong. Good guess. Right? Plus the log of b. Log of a over b equals log of a minus log of b. Logs are exponents. So when you see a subtract here, it's that same subtraction. These two statements are really the same statement, in one case using the exponential function, and the other the log function. And while it takes a little practice, you need to be able to go back and forth between them. Log of, this is a really important one, a to the n, it's just n times log of a. And I'm just going to throw this in, it's so basic. So if you have the log to some base b of b, that's what? That's the same as saying like 10 to the 1 equals 10. This is the exponential version. Well, if you make 10 to b. So you really want to be up on your laws of exponents and logs. And finally, we're going to do a fair amount later in the course with trig functions. Trig functions are all periodic functions. That means that if you take f of some x, some random number, plus p, the period of the function, it's the same as f of x. That's the same as saying, well, I've got my sine function, and this piece here, let's call that 1, looks the same as this piece here, and so forth. It's probably good to know the periods of the basic trig functions. Sine of x has a period of 2 pi radians, or if you want to lie back for a minute on degrees, 360 degrees. Cosine of x, the same. Their inverses, 1 over sine, 1 over cosine is the cosecant. Also 2 pi, secant, 2 pi. And then we have the tangent, which is just as a period of pi, and the cotangent, or cotangent, either the sine periods are pi. So they're going to repeat twice as fast. And you should know what the graphs of these look like. On the sine function here, cosine is just this moved over tangent. It looks like this. And then it repeats over and over. I'm not going to draw the cosecant. All right. The last little bit of review, and if you are not comfortable with this, I really encourage you to come to me and get an exercise where you practice this. We have our unit circle, and we have a number of angles, 30-degree angle, or pi over 6, 45-degree angle, pi over 4, 60-degree angle, pi over 3, 90-degree angle, pi over 2. All the equivalents over here. Here we have pi, and fourths pi down here. You should be able to figure out what all the trig functions are for all of these angles. I'm just going to do 2 of them real quickly here. Let's think about the sine pi over 3, which is a 60-degree angle. Remember, one of the first things I told you in this class was that this triangle, 30, 60, 90 triangle, is really important. It's important to know that if this is 1, this is a half, and this is the square of 3 over 2. And looking at this, I can immediately say, oh, 60-degree sine opposite over the hypotenuse is the square of 3 over 2. Right? And the cosine is a half. Find the secant, the cosecant, the tangent, all just looking at this triangle. Sine of pi over 4, well, that's 45 degrees. I should have mentioned that triangle. Everyone should be familiar with, this is an isosceles right triangle. If the hypotenuse is 1, then both sides are 1 over the square root of 2. So the sine of pi over 4 is the opposite over 1. It's 1 over the square root of 2. you should be able to like sit down if I gave you a list of all these, write down every function, value, exactly. Now, some of these you can get away with using your calculator. If I ask you what's the sine of pi, I'm sorry, the cosine of pi, you plug that into your calculator, it's going to tell you it's 0. Right? You look at the circle and you remember that x and y are actually cosine of theta, sine of theta. That's really obvious here. Right? Okay. Yeah. Okay. That's it. That's all of algebra, geometry, and pre-calculus in 1.5 days. Anything, anybody? No pauses.
I have a question.
Yes.
What is pre-calculus? Can you name some topics in there? And trigonometry?
Oh.
Pre-calculus?
Well, no. It's not like written in stone anywhere. Typically, in high school, people take 2 years of algebra and geometry, and then there's a class before you take calculus. It typically covers trigonometry, trigonometric functions, identities. It also goes into depth about functions, domains, ranges, rational functions, graphing them. Beyond that, historically, it's covered other things which I think are useful, like everyone know what a conic section is here? There's I'm just going to digress for a second. So the most common conic sections are a circle, which you should know is, well, it's x minus a squared plus y minus b squared plus r squared. That's a circle with center AB and radius r. There's the well-known parabola, which is, well, again, y minus a equals x minus b squared, x plus c. This is a parabola that has a vertex at AB, well, b plus c. There's also an ellipse, which has the form, I'm just going to use the simple form here, it's x squared over a squared plus y squared over b squared equals 1. A and B are the so-called semi-minor axes, this distance and this distance. And if you just change the plus and minus, you get a hyperbola, which has 2 pieces to it. These might show up in homework problems. It's not the main part of the course. If you're not familiar with the conic sections, again, come down, spend 15 minutes, half an hour, even an hour. Good to know. A lot to be said, but this is calculus, so. Did I? Yeah. Other questions?
Aren't you going to do the inverse of the sine?
Darn.
Yeah, we're going to need those. I'm going to be very brief on this. Let's just look at the sine function. The graph looks like this. It goes on forever. If you invert the graph along the x-axis, you're going to get something that looks like this. this has an obvious problem as a function. It's not a function, it doesn't pass the vertical line test. For each x, between, the domain is 1 and -1, between 1 and -1. There's an infinite number of inverses. So what we do with the trig functions is by convention, we cut off the domain of the sine function so that the inverse is a one-to-one function. So here we have the inverse sine. That would take half a class to go through all of this. If you're not familiar with it, you do need to be familiar with it. Inverse cosine, inverse tangent, that'll hopefully be adequate. You need to know, how do we adjust the domain, what's the range. In the case of the tangent, you get a function, inverse tangent, after you've restricted the domain of the tangent, you get a function that covers all real numbers. So you can find the inverse tangent of any real number. But for the sine, if someone says, what's the inverse sine of 2? You go, no, you can't do that. There's no angle that has a sine of 2. So, that's all I want to say about this. Again, important if you are not familiar with it, you're going to want to bone up on that. And I'm perfectly happy to assist you in that. Spectre. Yeah. Why don't we take a break now for 5 minutes? Review chapter 1, what we're going to talk about now. I think we'll find also in chapter 1. I put up an assignment for Tuesday. It's some pre-calc questions just to kind of get your feet wet. And I also requested you just 4 pages, just, get an introduction from Stuart, get another perspective on this. I'm going to just talk a little bit about what this class is going to be about. I know some of you who've taken calculus before are probably going to be familiar with all of this. So there are 2 main subjects you're going to learn in this class. One is called differentiation. Or finding the derivative of a function. The second we'll get to later in the class is called integration. Or finding the integral of a function. The indefinite integral. Both these subjects were discovered, I don't know if it's the right word, came about in the 1700s. Mostly they're attributed to Sir Isaac Newton and to Frenchman. Sometimes when you get old, certain things become difficult. In about 2 minutes, it's going to pop into my head, fellow. We'll just pencil him in for the moment. Leibniz. See? The importance of these 2 guys is that they used slightly different notation. And we're going to learn both of the notations because sometimes, well, just in general, Leibniz notation is better. sometimes it's cumbersome and unnecessary, and sometimes it's really good. So we're, I may mention them along the way at some point. Okay, so in the past, you've learned about, graphing lines, and your line has an equation y equals x plus b, where n is the slope of the line. You don't have to talk about the slope at a point because the slope is the same everywhere. In calculus, we're going to look at a more general function and the slope of the function at each point along it. I'm going to talk about what that means. In the past, you've run into, in geometry, the idea of a tangent to a circle. Recall, you have a circle and a radius to a point. The tangent is perpendicular. In calculus, we're going to take a look at a more general function and find, again, this idea of a tangent at a point. And in particular, the slope of this tangent is the slope that I'm referring to here. At each point, we could find a tangent, it would have a slope, and that would be the slope at that point. And if you combine all those points, that's a function, which we're going to call the derivative. Okay. In the past, especially if you take a physics course, but maybe in math, you run into so let's say here, let's say laws of motion. You would run into the idea that distance equals velocity times time, where velocity is not changing. In calculus, we're going to look at the idea of distance as a function of time where velocity is varying. Possibly also, if you know about acceleration might also be a function. So we're going to look at something a little more general way of looking at motion. So in the past, in geometry in particular, you've learned the area of various geometric objects, even kind of general polygons, and of course a circle. And in calculus, we're going to be looking at more general shapes and finding the area within them. And finally, angles. You probably use degrees. You may have learned radians. And in calculus, you're going to see, I think I said this on Tuesday, radians are the right way to measure angles in math. Okay. So, as I said, we're going to look at kind of a general curve and some point on that curve, and the idea there's a tangent, a single line that goes through just one point. And we're going to, having defined this for all the points, we're going to call the function we get that produces that slope the derivative. We have some different types of notation. We have some function x, so this is f of x. The derivative we're going to refer to by putting an ampersand here, not ampersand, apostrophe. That's the Newton way of writing this. The Leibniz way would be to say d dx of f of x, or if we're talking about a function in terms of y, we might write dy dx. This is very reminiscent of something we've run into before, your slope being delta y over delta x, delta. These are sometimes called infinitesimals. It's generally, it's going to be a mistake to try and think of this as a fraction, right? These are two things that are of size 0 over each other. It doesn't make sense. Just think of this as, at least for the time being, as notation. It's just a way of saying the derivative of f. Okay. I want to look at some very basic derivatives, even though we really don't have the mechanics yet. But there's some derivatives we can look at and discover some things. So let's start with a really basic function, f of x equals some constant c. We're all familiar with what that would look like if I graph it. I'll use color here. All right, so that's c. So let's think about what the derivative of this function is. Well, 0, the slope is 0. 1, the slope is 0. At every point, the slope is 0. So we can say pretty unequivocally the derivative of this function is 0. We would graph that. It's going to look real similar, isn't it? Just a straight line along the axis. All right. So we've done our first calculus. Okay. Noteworthy is if my function were 0, which it could be, you get the derivative is the same function. Right? This will come up later when we look at finding multiple derivatives, second derivatives, third derivatives. If you have a polynomial, eventually you get down to a constant, you get down to 0, and that's it. Okay, let's try a little more complicated function. Let's try y equals mx plus b, which of course is a straight line. Delta y or delta x. X is our slope. B is our y-intercept. So let's think about the slope along this line. Well, at 0 it's m, right? The slope. At 1 it's again m. So if f of x is mx plus b, its derivative is just m. It's a constant. So again, we can do a little, even, knowing the concept with all we know at this point, we can do a little calculus. We have two derivatives now that we know. Constant function and a linear function, a line, are pretty straightforward. I want you to notice that in this derivative, b doesn't appear. If we had another function, c, going to look like this. Okay. Same slope, it's parallel. So that suggests something here. Okay. If the derivative of mx is m, well, sorry. And the derivative of constant b is 0. Well, that suggests something here. If we have f of x equals mx plus b, it kind of suggests that this is the derivative of this is our function. Its derivative is the derivative of mx plus the derivative of b. Because this is 0, right? And this is just n. Now, we're way ahead of ourselves here. This is just suggestive of this. It's going to turn out this is true. It's nice. It means if you have some complicated expression with a bunch of terms, you're adding things up, you can find the derivative separately. But we haven't gotten to that point yet. We have to demonstrate that first. Okay. We're going to do one more derivative that's we can do. It's kind of sophisticated. We don't need calculus because we all remember our geometry lessons. We're going to take a look at the graph here. This is a circle of radius 1. But I'm only interested in the upper half because I want it to be a function. So in that case, f of x is the square root of 1 minus x squared. Just in case you're not familiar with where I got that. The equation of a circle is x squared plus y squared plus 1. This has radius 1 equals 1. If I solve for y, I get y squared equals 1 minus x squared. And if I find the square root, minus x squared. So that's where this comes from. So I would like to know what the derivative of this function is. It seems awful sophisticated at this point. We don't know anything about derivatives of squares or square roots, or in this case, a composition of them, but we do have geometry. So if we pick some point, xy on here, we know that the tangent to that point is perpendicular to the radius. So let's find out what the slope of the radius is, because we've remember that perpendicular slopes are related how? Very quiet. I don't know what to draw here. Perpendicular side. Negative reciprocals. Two lines have slopes that are negative reciprocals or perpendicular. Okay, so first let's find out the slope here. We have some point x here, and this is y, but we know what y is. And delta y over delta x is going to be square root of 1 minus x squared over x. That's going to be our slope of our radius. Like, yes?
I have a question. So why couldn't you just change its fraction in the beginning? Like, you know how like the square root could have been like that?
Would you do me the honor of showing me? I'm not quite.
No, it's just like, you know how it's like.
Don't be
square root-
scared. They don't throw things. You haven't so far. Say again. Maybe I'll understand in a second.
Like, you know how it's square root of y over x squared?
Square root of
Like the equation.
y over x.
Oh wait, no, I read it wrong, sorry. Square root of 1 over x, 1 minus x squared.
Mm-hmm.
Okay, that's the equation. Why couldn't you just have written it as 1 minus x squared?
Well, that's what y is here.
No, I'm saying, why couldn't you just write that formula as 1 minus x squared in parentheses, and then to the power of 1, like 1 over 2? If that
Oh.
makes sense.
Yeah, I could do that.
Okay.
Yeah, that's fine. If you prefer that. It's exactly the same thing. Yeah.
Then I'll
We'll keep your notation. All right? No, I'm good. I'm good with that. Okay. So that's my slope of my radius. What's the slope of my tangent, which is perpendicular? It's going to be the reciprocal but with a negative sign. I'm going to rewrite that. F prime of x equals negative x over 1 minus x squared. Oh, that's pretty good. What we did is we used our geometry knowledge. We didn't have to use any new calculus. And here we have a pretty sophisticated expression for the slope of any point on this semicircle. Now, when you do something like this, sometimes you like go, well, did I get that right? Does this make sense? So let's just, just do some. I apologize. Can you see over?
Yeah.
Can you just fine? Okay, all right. All right. So let's look at 0, right? So what do we know about 0? What would the slope be at 0 of the tangent? 0. Well, let's check. Minus 0 over 1. Oh, good. Okay. Let's try at a 45-degree angle here. So that would be, what would x be there? It would be 1 over the square root of 2. So let's see, minus 1 over the square root of 2, or 1 minus 1 over the square root of 2 squared the square root. So that's, what do we get? Probably shouldn't be using red for this. That's a quarter. 1/2. So that's 3/4 square root 3/4 minus 1 over the square root of 2 over square root of 3 over 2. So divide by a fraction, multiply by the reciprocal. 2 over square root of 3. I don't think I got the right answer. This should be what? Should be -1. You did something wrong. You can investigate that. I know where I went wrong. This is right, I know that. Okay, one last kind of check. What happens is, as we get over to the edge here, we get to 1 or -1. Well, the slope is going to infinity, these are vertical. Well, of course, if you plug 1 in here, you're going to get 0 in the denominator. So that's what you'd expect, right? You'd expect the slope to go to infinity. All right. All right, so that's the last of this kind of easy calculus we can do without doing any calculus. Now we have to look at the real thing. So we have some function. We can't just, arbitrarily say, oh, we know what the slope is. But we can approximate it. We pick some other point on the curve, and we draw a straight line through it. Call one line through any 2 points. We can then, determine the slope. We'll call that M1. And that gives us an approximate value of the slope at this point. Well, wherever we pick it, there's still room here, so we can pick another point. And again, we can draw a line through these. We can get our M2. And except it doesn't look that way in my drawing, it would be a better approximation. And you could keep doing this, right? You just get closer and closer. It's actually, let's kind of describe this here. This is some point C, and to whatever point we're approximating it, we'll call the distance from C to that point delta x. So, okay, we have 2 points here. We have C and function at C. And we have C plus delta x and the function at C plus delta x. So we know how to find the slope between 2 points, don't we? Right? Delta y over delta x. So let's find out what that is. So delta y, that's f of c plus delta x minus f of c and delta x. That's c plus delta x minus c. Oh, well, that's just delta x. So what we're doing here is we're moving this point closer and closer. We're making delta x get smaller and smaller to this expression. Now, if delta x becomes 0, this is undefined, so it's not useful. But this brings us to the first important subject we're going to study in calculus, which is limits. We're interested in what this expression looks like as x gets very small, as we get very close, because that limiting value is going to be what we call the slope here. And that limiting line is going to be the tangent line. All right. And that brings us to the subject of limits. So let's talk about limits a little bit. We have some function. And I have some x value c. And I'm interested in the value of f of x close to c. Now here's kind of a stumbling point for a lot of people. Say, well, how about f of c, right? It turns out a lot of cases, the value that f of x gets to as you get close to c is f of c. But it's exactly the case where that doesn't work, where you get a 0 in the denominator. That's interesting, right? So again, we're not really interested, here's the values of f of x, here's f of c plus some delta x, and here's f of c minus some delta x. Right, so here's delta x. So we're interested in what this function becomes as we get close, regardless of what its value is at c. That's actually unimportant. All right, so we need some notation here to describe this. I'm going to use the arrow here to mean approaches. And the first version of this terminology is we're going to write the limit as x approaches c of f of x equals, and then I'm going to use the letter L to mean a limit. Or alternatively, I might write f of x approaches L as x approaches c. So you can read this in different, in those different ways. You can say the limit of f of x is as x approaches c is L, or as x gets close to L as f of x gets close to L as x gets close to c. Or you could say f of x approximates L as x approximates c. I've said this already twice, I'm going to repeat it again. It does not matter what f of x is defined at c, or if it is even defined at all. Now,
Question.
yes,
Good question. So just to clarify, oh, sorry, what was that?
okay.
And just to clarify, C is a given that's going right?
It's some c, yeah.
Okay, so.
It's a constant. I mean, some students like numbers, so we'll just say 1. But it would work for 2 or 3. Yeah. Okay, let's look at a function. It's kind of easy to understand the limit of. Okay, the function is f of x equals x cubed, let's see, minus x squared, x minus 1. And I'm not going to be coy about this. This is x squared times x minus 1 over x minus 1. So let's think about what the graph of this looks like. Looks a lot like f of x equals x squared, which is our parabola. But at 1, there's kind of a hole in the graph there, right? It's undefined there. So as we get close to 1, our function gets close to 1 squared, which is 1. But the function is not defined there. It's defined, it needs to be defined everywhere nearby here for there to be a limit. And it is. So we can write limit as x approaches 1 of x cubed minus x squared over x minus 1 is equal to 1. No question about it. Right? Doesn't matter that the function is undefined there. You can get as close as you want to that point, and you just get closer and closer to 1. Now, not all functions are nice. Let's look at a very ugly function. No, this isn't that ugly. We're going to look at the ugly function later. Let's look at this function. F of x equals, this is a piecewise function. 1, if x is greater than some constant. And minus 1, x is, we're going to say x is greater than or equal to c. And less than c. Okay, and we're interested in the limit as x approaches c of f of x. Now I want you to note something here. This function is defined at c. It's 1. So if we graph this, right, we're going to see here's c. So it's c and greater, it's 1. And then less than that is minus 1. So what's going on here? Well, as we get close to c from this direction, we get close to 1. As we get close from the negative direction, we get negative 1. So this does not have a limit. Not a sign. And typically in homework or on tests or discussing it, we'll use the phrase D and E. not exist. Right, this limit does not exist.
Question.
Yes?
Like, what is the point of finding the limit? Like in a real world situation?
Ah. Well, go back in time. We'll get there. We had a picture here where we had a ratio, a fraction, where delta x was going to 0. So when delta x got to 0, it's undefined. We'll get back there. Okay, so you can have a derivative of this function everywhere but at c. Over here it's 0, and here it's 0, but it's undefined here. So there are circumstances where a limit does not exist. We're going to look at another one. F of x equals 1 over x minus c. It's a rational function. This is a polynomial. It's kind of a boring one. This is a polynomial that's at least linear. At point C, oh, I'm just going to put in a number. It's 5. There we go. There's going to be an asymptote, and the function's going to look like this. If I put in a number greater than 5, it's positive, and for very large x, it's going to go to 0. That's a horizontal asymptote. The same thing if you get very negative, it's going to get very close to 0, but coming up from the negative side. As you get to 5, well, if you come in from this direction, from the right, from the positive direction, this is going to get very large. And if you come in from the negative direction, 3, 4, 4.5, and so forth, it's going to get very negative. So here it gets arbitrarily large, here it gets arbitrarily small. The limit, as x approaches 5, 1 over x minus 5, does not exist. There's no number that we get close to here. All right. One more example in the does not exist category. This is the ugly function. We're going to run into now and then because it demonstrates certain interesting things. One, if x is rational. X is a fraction. 3/4, 5/8. 0, x is irrational. Square root of 2, square root of 3, pi, e, one of those numbers. What does this function look like even? Really, I mean, we're always like kind of making a representation here, draw lines, which are really not infinitely thin, but to get an idea. This is kind of like a dotted line here, except the dots are infinitely close together. And you get another dotted line down here at 0 with all the irrationals. So if I ask, we'll pick 5 again. What's the limit as x approaches 5 of f of x? Well, what happens is you get close to 5. F of x is just jumping up and down like crazy. It doesn't get closer to some value. Note again here, f of 5 since it's rational, is 1. But the limit does not exist. All right, so we saw an example where a limit exists, but the function isn't defined at that point. We've seen 2 examples where the function does have a value at that point, but there's no limit. And we've seen cases where neither is the case. It's not defined and there's no limit. All right, let's see where we are. Okay. Right. So before I go into the next section, I just want to wax philosophical for a second. So you all know when you were learning math, like go way back to, say, first grade, what do they do? You count, right? 1, 2, 3, you learn the numbers. And they didn't tell you at that time that there were other numbers. Maybe you were precocious and you knew about a half. But eventually they said, oh, well, we've got these fractions, halves, whatever. You learned a little bit more. And then one day in probably algebra, maybe before, they said, well, they're negative numbers. You thought, that doesn't make any sense. But, wait a minute. I overdrew my bank account $10. That's like minus 10. It all kind of fits together after a while. But you get the idea after a while that they keep putting new things into math that like you didn't know about and don't always make sense right at first. And you wonder, where is this all going to end? Square root of -1? No, it didn't end there. We get these irrational numbers. So there's a ceiling. There's a ceiling in math. It's the top. It's like it doesn't get any more complicated. And we're about to hit that ceiling. And the reason I'm just wasting your time just chatting about this is I'm going to show you something. It will not be on the exam. You are not expected to absorb this and regurgitate it. And I hope you understand it. I hope I can present it in a way where some of you will get excited and go, that's it. That's the ceiling on this topic in math. I saw it, watched it, I understood it. You don't have to be able to do it. I don't think anyone in here is pronouncing themselves a math major. If you were a math major, you'd take a couple other courses and you'd get to a class called analysis, and you'd see what we're doing here. But I would skip this because it's unnecessary, except that we're going to do some proofs later where we may use this. And if you've never seen it before, like what? You're going to get nothing from that proof.